Alright, so welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your chemistry teacher for this session. So what we're doing at OneClass is we're going through this kind of session of verifying some frequently asked problems in both mathematics and chemistry, in both the secondary level as well as in the university and college level. So what we have today is I have a series of 10 questions in high school chemistry. So if you're looking at the Ontario curriculum, it's anywhere from grade 10 to grade 12, or if you're tuning in from the US, it's basically the junior level as well as the senior level chemistry courses. My name is Joey. I'm currently an Ontario school educator. My teachable subjects are chemistry, music, and soon to be mathematics after I finish up a teachable. So without further ado, let's get started on today's problems. Again, we have 10 problems per day, and we're going to go through these solutions together. So our first question goes, predict the ground state electron configuration of the following ions. It says write answers in abbreviated form. So this is concept of electron configuration. So what we have here is we have Ru2+, and we also have W3+ as well. So this is ruthenium, and W, I believe, is some type of metal. I'm not sure what W is actually, so maybe I'll have to look at my periodic table. But either way, what we have here is, W is tungsten actually. So that's it over here. Okay, so we have ruthenium 2+ here. So ruthenium, we know here is, if you look at periodic table, it's in the metal section, and we know that ruthenium is atomic number 44, right? So what we can do is we can write the electron configuration for ruthenium first. So let's write ruthenium here. And it's going to be the electron configuration for ruthenium. So I'm going to go, again, I have the 1s2 electrons here. I also have 2s2, because 2s2 would be these two electrons. 2p6 is this block over here. The noble gases are cut off, but it's 2p6 here. 3s2 and 3p6 for both the third period. 3s2, 3p6. We have 4s2 here, signifying those two elements, and then this entire block here is a 3d10 block here. So this is the D block here. So this would be 3d10, and then we're gonna have 4p6 for these guys over here. So this is 4p6, and then 5s2 is these two electrons here, and then we're gonna make our way to ruthenium. So we have 5s2. And then we have 1, 2, 3, 4, 5, 6. So it's going to be 4D and then 6. And this is just ruthenium. So then it's asking us the ruthenium it has a charge of 2+ here. So it means my electrons here, I'm gonna remove 2 electrons from this 4D6 electron here. So I'm gonna erase the 6 on this guy here, and this will become, because right now it's a Ru atom here, I want a 2+, so therefore I need to remove 2 electrons, so I get a 2+ charge here. So 6 minus 2 here is going to be 4. So this here is going to be the electron configuration for ruthenium, and what we want to write here is we want the ground state actually. So we want the ground state here. So we all actually want Ru and not 2+ here. So this actually goes back to 6. So I didn't read the question, sorry. So this here is actually going to be a 6, because we want these in ground state. So therefore these are it's going to be a 46 on here. So that's okay. And what we can do is we can find the abbreviated form by taking the noble gas that we found here, and we can write the short form, the shorthand for electron configuration. So in this case here, ruthenium is here. So we're gonna go back to the closest noble gas, which is krypton. So this can also be written as Kr, and then we can write out the electron configuration. So after Kr, we have again 5s2 and then 4d6. So 5s2 and then 4d and 6 here. So this is electron configuration for ruthenium, and as you can see, this here is correct. Yeah, this guy is good for the ground state. And what we can do with W here, this is the part B of this problem. This is W3 plus, right? This is tungsten. So what we can do with tungsten is we can actually do the exact same thing, right? So W, I know it's here, so we can go all the way back to the closest noble gas, which is if we go backwards here, I'm going towards the 5th period, and I can see xenon here is the closest one here, right? So I'm going to write xenon here, and then what I can do is I can write out the electron configuration here, right? So I have 6s2, which is these two guys here. And then it's going to go to this lanthanide block, and this guy here is the F block, and this is the 4F block. It's 4F, and it's the F block, I believe, has 14 electrons as stated here, which is great. So 4F 14, and then we're gonna have this block here, which is 3D, 4D, and 5D. So it's 1, 2, 3. So 5D3 here. So this here is 5D3, which is great. And this is the electron configuration for the tungsten 3+. So this solution here is correct. So these two guys are the correct answer. And again, the solution is great. So the solution is correct. Good analysis here. So the trick question here is about ground state. And when we talk about the ground state, we care about the electrons. We're not altering the amount of electrons in ground state. So that's kind of the trick question over there. So this is number 2. I don't like this color here. Switch it up here. Okay. Number 2. Why is fluorine a gas, bromine a liquid, and iodine a solid in room temperature? So it's actually a pretty complex question when we talk about this question here. We're talking about fluorine, bromine, and iodine here, and these guys are all halogens, right? So these guys are all halogens. So when we talk about these halogens here, we can look at our periodic table. So we have F, which is a gas. We have Br as a liquid. And then we have iodine here, which is a solid. So if we look at our periodic table here, as you can see, fluorine and bromine here is a liquid, and iodine here is a solid, right? As you can see, the letters here, this here is in kind of burgundy, which represents gas. Bromine here is kind of liquid form, which is blue, and iodine here is black, so it represents the solid here. And the reason it's asking is why are they gases? Why are they liquids, and why are they solid in room temperature? Well, if you look at these gases here, or these halogens here, you have these guys here are diatomic, right? If you think about their diatomic molecules, you have Hoff, Brink, and Cl here. So these are all a list of diatomic molecules. So you have F2, Br2, and I2. And then as you can see here, these guys here don't have, in terms of intermolecular forces, we only care about the van der Waals forces or the London dispersion forces. So all of these guys, and let me do this in orange here. All of these guys here possess London dispersion forces. And when we talk about London dispersion forces, many of these guys here depends on the atomic radius of these guys here. So as you can see, fluorine here is a gas. So, and fluorine here is, it has atomic mass of 18.98. Bromine is 79.904, and iodine here is 126.90 here. So as you can see, as we go down here, down the periodic table, our atomic radius is going to increase, which means the London dispersion forces also increase. So given those two things, when we talk about the states of matter here, if the London dispersion forces are increasing, that means they're going to be, these molecules are going to stick more together given the same temperature, in a constant temperature. So if I say in constant temperature, because the London dispersion forces are stronger as we go down the periodic table, the states of matter are going to be, the molecules are being more tightly bound together. So therefore, it's in a solid form. So as you can see, this guy here is solid form, and we have this iodine here has the highest amount of London dispersion forces. So the molecules are going to be closely packed together. So therefore, it's going to be solid form. And then it's going to be liquid for bromine because it's this, again, the atomic mass here is slightly smaller, and fluorine here has the smallest atomic mass here. So it's going to exist as gas because it has less London dispersion force holding it together. So in terms of a gas, it's more free to, and it takes in more volume in that case. So in this, again, this is all in room temperatures because we're comparing this in constant temperature. So that's why fluorine's a gas, bromine's a liquid, and iodine's a solid here in room temperature. So let's see here, all of them are halogens, which is great, and we only care about the van der Waals forces, which is good. So higher the van der Waals forces, the higher the energy required to break these bonds. So therefore, it's in a solid form, and then bromine's a liquid, and fluorine's a solid here. So this solution here is correct. It kind of goes back to this idea of intermolecular forces and how the bonds work and how much energy you need to break those bonds here. So the solution here is correct. Okay. Number 3. It says carbon disulfide is prepared by heating sulfur and charcoal. The chemical equation is Kc is 9.40 at 900 Kelvin. How many grams of CS2 grams can be prepared by heating 9.26 moles of S2 gas with excess carbon in a 6.05 liters vessel held at 900 Kelvin until equilibrium is attained? Okay, so what we're going to do first is we're going to first look at the chemical formula, right? So we are heating, we're heating S2 with excess carbon here. So what we can do here is we can say that S2, I'm going to write our chemical equation here. So S2, oh, that's not what I want. I keep accidentally clicking this here. So S2 is in gas form here. Or sorry, this is, yeah, S2 in gas form. Plus we have solid carbon here, also in gas form. Is going to create here, or maybe be in equilibrium here with, and this is with CS2 gas. So carbon disulfide here. And what we can say is the Kc here is going to represent the concentrations of, in this case it's in gas form. So basically you can talk about them in partial pressures, or it can or it can be in concentration. But for now I'm going to stick to concentration because we're not given a pressure here. So this is going to be the concentration of our products, which is CS2, carbon disulfide, divided by our reactants here, which is S2 and C and solid carbon. However, solid carbon doesn't play a part in our reaction here because it's a solid guy. So we care about the S2 only here. And these are both in gas forms. So we know that the Kc here is going to equal, it's going to equal 9.40 at 900 Kelvin, which is good. And what we can solve for is we can first solve for the moles of, we can solve for the molarity here of our S2, right? Because we have moles here, and what we have is our volume as well. So let's solve for that. So we can solve for the our concentration of S2, so we can solve for our concentration of CS2 here. So let me do this in blue here. So we have the concentration of S2 is going to equal the moles of S2 divided by the volume We have the moles here is going to equal, let me do this actually on this side here, and the moles is going to equal, we have 9.26 moles of S2 divided by our volume, which is 6.05 liters here, and this is going to equal 9.26 moles divided by 6.05 is going to equal 1.53 molarity, which is what they got here, which is great. It's 1.53 molarity of S2. So therefore, what we can do is we can actually isolate for our CS2 here. So let me go back, change this. So this is going to equal. So we know that our Kc here is 9.40. So we can say that this is 9.40, which will also equal the concentration of CS2, which we don't know here. And what we can do is we're gonna have to perform an ice table actually. So let me redraw this actually. So this here is our this is our equilibrium expression. So what I'm gonna do is I'm gonna draw an ice table real quick. And I have S2 here, which is our 1.53. So we have S2, and then we have C, which we don't really care about. We have CS2 here. So I'm not going to include C in our ice table because it doesn't play a part in our equilibrium expression. So we're going to start off with 1.53 molarity here. We're starting off with 0 here, minus X. I'm going to add X here. So I have 1.53 minus X and X here, like so. So therefore, our Kc equilibrium constant here is going to, we have 9.40, which is our Kc. So we're at 9.40 is going to equal the concentration of CS2, which is in equilibrium, which is X, divided by our concentration of S2, which is 1.53 minus X. And all we're going to have to do is isolate for X here. So I'm going to multiply both sides by 1.53 minus X. So I'm going to get 14.382 on the side minus 9.40x equals X here. So I get 14.382 equals, this would be 10.940x. So therefore X is going to equal 14.382 divided by 10.4940, which is 1.31. I'm just checking my math here. They got 14.38, which is good, minus 9.4 equals X. So this is, oh, I added a 9 here. My bad. This is a 9. This is 10.40, sorry. I think I added a 9 there by accident, so my numbers got thrown off. So this is a 10.40x, and I can just simply divide both of these guys here to get my answer, which is going to be 1.38. And this is the molarity of our CS2, right, of our carbon disulfide. And what we're doing is now we're trying to find we want to find the grams. So if we're given our molarity, what we can do is we can find our moles now, right? So I know that C, our concentration of CS2, is going to equal the moles of CS2 divided by the volume. So I know that the moles of CS2 is going to equal simply the concentration of CS2 times our volume here. So I know that this is 1.38 molarity times our volume, which is 6.05 liters, which is going to give me our molarity, our moles, which is 38 times 6.05, 8.39, 349, sorry, moles. And then what we can do is we can find mass by simply saying, we know that moles equals mass over molar mass, so therefore mass equals moles times our molar mass. So we have 8.349 moles times the molar mass of carbon disulfide, which is, and I can calculate that, so carbon here is 12.011 plus 2 sulfur, so 2 times 32.06. And this is going to equal my my grams of carbon disulfide that's being created here, which is 8.349 times 12.011 plus 2 times 36.06, which is 64.12. So I'm going to get a value of 635.6 grams. So this here is the correct answer. So I would get 635.62. This is in grams. So this here is my solution. So this solution is very, very close, 6.8, which is probably due to our molar mass calculations here. So this solution here is correct. Let's get analysis as well. This is number 3. Number 4 is to select the correct IUPAC name for the following branched chain alkane. So let me try to write this. Oh, this is a very, very big guy here. Let me see. Let me do the line diagram instead, because writing the CHs would be kind of tedious here. So I'm gonna count 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I have a methyl chain on the second carbon here. And then I have a methyl chain on this carbon here as well. And then on the 1, 2, third carbon, it's going to be bonded to some type of carbon here, which is also bonded to another carbon. And this guy is bonded to a propyl chain. So 1, 2, 3. And this guy is bonded to 1, 2, 3, 4, 5. So a pentyl. 1, 2, 3, 4, 5. And within the pentyl chain of 1, 2, 3, it's going to be bonded to an ethyl. So 1, 2, 3, bonded to an ethyl, like so. So now it's asking us, what is the correct IUPAC name for this guy here? So this here is our line diagram. And what we can do with this guy here is we have to figure out, okay, where do we start counting? Well, it looks pretty daunting to see this firstly. So let me look at our side groups here. So what we're going to do is we're going to minimize those numbers. So I see a propyl chain, which is pretty big here. And then this here, I can make maybe this guy here the longest chain. I'm picturing kind of this guy here as the longest chain, because this here is a pretty long chain here. And then I can make these guys, this one would be this would still be a propyl chain here, and this one would be ethyl, and this one would be a isopropyl chain here. So maybe that's probably the way to go through. So I'm going to try this, and I'm going to label this from 1 to 1 starting here, because I want to put priority on this propyl chain here. So let's go from 1, 2, 3, 4, 5, 6. This would be 7, 8, 9, 10, 11, and 12 here. So this is a dodecane. So we know that this here, it's going to be either A or a D will be our answer here. And then within this dodecane we have, let me write this down here. So I have 3, I'm going to have an ethyl group here. 3 ethyl group. On carbon 6, I have a propyl. This chain here is a propyl. On carbon 6, we also have a methyl group, right? So a methyl group on carbon 6. And then on carbon 7, we have a isopropyl, or you can say 1-methyl ethyl. Doesn't really matter. This is carbon 7. So 1-methyl ethyl. And then finally on 11, we have another methyl here. So these guys here are going to be my my numberings for if I labeled it in this order here. So let's look at the answers here. So we have 7,10 diethyl. So 7,10 diethyl, which doesn't make sense here. So this here is 10 ethyl. But this one's not a 10 here. So let's see. Would I have to label it from, let me try from this way actually. So 1, 2, 3, 4, 5, 6. This would make it a 7 instead of 6. So this one would have been a 10 here. So let's see. I'm either labeling it from 1, 2, 3, from this way, from right to left, or from left to right here. That's what I'm trying to figure out. So I have 1, 2, 3, 4, 5. This would be a 6 for the isopropyl group. This one would be a 7. So it's kind of a tie here between those two. Because I want the 6 actually, let me do this in a different color here. So it's there's either 2 numberings here. And these are the numberings I'm going to go for. 4 here, 5, 6, this is a 7, 8, 9, 10, 11, and 12 here. And the orange ones are the first fingerings if I were to go from right to left. Oh, you can't see this actually because I'm blocking the ethyl group. Sorry, there's the ethyl group here. My bad. Let me write that down actually. There's the ethyl group here that you can't see. So because my face is blocking it, sorry. But basically the green numbers are if I label from left to right, and the orange numbers are from right to left. And we're trying to figure out which one's the best one here. And in this case, if I'm looking at the answers here, I have a 10 ethyl here, which is good. And I have a 2,7 dimethyl here, which is good as well. And this is 6 1-methyl ethyl, which is this guy here. 7 propyl, which is this 7 propyl here, and this dodecane. So in this case, I would actually say that I guess in this answer here, I would go from left to right here so that it fits this answer here. So let me erase these guys here, and we're gonna go through with the green numbering system here. So we minimize. We want to put priority on this isopropyl group here. So this would be, so I would have a 2 methyl here, a methyl and 2. 6 here would have a isopropyl, or I can say 1 methyl ethyl. On 7, I have a methyl group, as well as a propyl group. And then on 10 here, I have an ethyl. So if I were to label it from alphabetical order, and again, the parent chain here is dodecane for 12, a 12 carbon chain here. So if I were to label this, I'm going from alphabetical order. So this here, I'll put ethyl first, right? So this would be, 10 ethyl. So 10 ethyl, and then next I would have the dimethyl group, because the M comes next here, the dimethyl group. So this would be, and I have 2 methyl groups, right? So I have 2,7 dimethyl. So these guys are good. 10 ethyl is good, and then I have 6, and then this is 1 methyl ethyl. Or you can say isopropyl, it's up to you. In this case, I'll do a methyl ethyl. 1 methyl ethyl. That's good. And then 7 propyl, and then dodecane. So this would be 7 propyl, then dodecane. So this here, my answer here is D here. So as you can see, the answer here is D, which is great. And they labeled it from left to right, like what we said before. So again, the numbering, it takes a very, very long time for us to figure this out, because it's a very, very big chain here, but we also have to test from left to right and from right to left to see which numbering system works out for us here. So solution here is correct. Good analysis. All right, what number was this? This is number, I believe it was number 4, so this is number 5 here. It says rank these substances in order of increasing solubility here. Okay. So I want most soluble to least soluble. So most soluble to least. And I'm giving four options here. So I have the first guy here is CH3. CH3, CH2, and there's a 5 here, and then OH. I have a CH3, CH2, 3, and then an OH. And then I'm going to look at the right side here. I have CH3, CH2, CH2, OH. And then finally a CH3, CH2, OH. It's asking us which one is the most soluble, which is to the least soluble. I'm going to rank these guys here. So let me give them numberings here. So I have 1, 2, 3, and 4. So as I look at these compounds here, I have an alkane group here. All of these guys here are alkanes. Sorry, all alkanes here. So straight chain alkanes, which is great. And then I have a hydroxyl group, right? These guys are here are alcohol groups. So all of these guys here are alcohols because they are, I see the hydroxyl groups, and we all have alkanes. So basically, when we're talking about solubility, we care about the intermolecular forces that exist in these compounds here. So as you can see, since they're all alcohols, they all have hydrogen bonding, right? Because of the hydroxyl, the hydrogen on hydroxyl groups can make the hydrogen bondings with our oxygen atoms in solution here. So the hydrogen bonding exists. We also have a dipole-dipole, right? Because the electronegativity difference between carbon and oxygen exists, right? So we have a large difference of electronegativity. So therefore, there's a partial positive on this carbon here. So you can say that this carbon has a partial positive. This oxygen has a partial negative. It's pulling electron density away from it, which is great. And then obviously we have London dispersion. So keeping these guys in mind, what do we care about here? So all these guys affect solubility, right? So if we look at hydrogen bonding and dipole-dipole forces, all of these guys have hydrogen bonding and dipole-dipole forces, right? Again, we all have hydroxyl groups, and they all have the electronegativity difference between the carbon and the oxygen. So these two guys are good because we have all of them have everything. But the London dispersion forces vary between all these guys here. And the reason why is that London dispersion here is the weakest here, right? Number 4 here has the weakest London dispersion forces. And number 1 here has the largest. The reason why is that it has a longer alkane chain. This one has a 5 chain, right? So this one has the strongest LD forces. And as we know that, because we know that this one has the weakest LD forces, this has the strongest one. This one here is particularly more hydrophobic, right? Because alkane chains are non-polar. So these guys here are all non-polar. So let me do that. Here, these guys are non-polar. And this end, the hydroxyl end, is obviously the polar end, and that's the point that's soluble, right? So if you want to label these guys here, which one's the most soluble? Well, number 4 is the most soluble here. So the most soluble is number 4 because it has the weakest. You can say it has the shortest alkane chain, so it's less hydrophobic. So this one would be 4. It would go 4, 3, 2, and 1. So this here is the order from most soluble to least soluble, and this here is our solution for this problem. And again, the longer the alkane chain here, the more nonpolar the molecule is going to be, because again, it's pulling electron the difference here away from our hydroxyl group here. So the carbon is becoming more and more important, more positive. You can think of it that way. So again, it's 4, 3, 2, and 1 here. So again, it says here solubility depends on like dissolved like, which is good. So we have here, therefore, butanol is much alike to water molecule than hexanol. Butanol is more soluble than hexanol. So as you can see here, it's 4. So ethanol is the most soluble here, and then it's propanol, and this here is butanol, and this here is a hexanol here. So this solution here is correct. And again, I think they have the first, or actually they mixed up these two actually. So the person who submitted this mixed both of these up, and they didn't actually talk about this solution as well. So this solution is partially correct because they didn't figure out the other guys here. Most soluble to least soluble. So it would be ethanol, propanol, butanol, and hexanol. All of the compounds have a hydroxyl group. However, the longer the alkyl chain, the more nonpolar the compound becomes, making it less soluble in water. Therefore, ethanol is the most soluble, while hexanol is the least soluble in water. So the solution is partially correct because they only answered the first two. So anyways, in this case, I'm going to say incorrect because they're missing some information here. Okay, that's number 5. Number 6 is, how can I draw the Lewis structure for ClO2 1 minus here? So number 6. Let me see, 6, 7, 8, 9, 10. Yeah, number 6. So I want the Lewis structure for ClO2, 1 minus. So what we're going to do here is we are going to look at our Lewis structure here. So we have ClO2 minus 1 minus here. So as you can see, what we're going to do is we're going to put again the most electronegative atom in the middle here, right? In this case, it would be chlorine. So ClO. And what we can do is we can fill out O here because there's two O's here, right? So we can say O and O here. And what we can do is we can draw out the electrons, right? So we have 2 oxygens here. So we have chlorine itself has 1, 2, 3, 4, 5, 6, and 7. And then we have oxygen here, which has 6, right? So we have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6 here. And what I need to do is, again, I want to make a bond between these two guys here, right? So I'm going to make a bond here and make a bond here. So I'm going to fill these guys here. So these guys are going to share electrons here. And these guys are going to share electrons here as well. So let me rearrange these valence electrons for you to see that, to make this a bit more obvious here. So Cl here is going to share, and I'm going to have one of these guys here as well. So these guys are going to share, and these guys are going to share. So what you're going to get is you're going to get O bond to Cl bond to O. And again, this chlorine, because it's not used to making 2 bonds here, is going to possess the negative charge here. So this here is going to have the negative charge. So this here is a Lewis structure for ClO2 minus. And as you can see, this solution here is correct. But I believe that they didn't write the negative charge here as well. So again, this 1 minus charge applies on this chlorine here. Or sorry, on this, yes, it would be on, well, it's technically onto the entire kind of structure here, just because oxygen usually likes to make 2 bonds, and this oxygen usually likes 2 bonds here. So this 1 minus appears to be a whole charge. But in this case here, it doesn't really matter to the extent of this question, but the solution here is correct. Because again, I have OCl, O bond Cl bond O, and again, these guys are sharing our electrons here in the Lewis structure. So this solution here is correct. Good analysis here. Okay, that's number 6. Number 7, I'm assuming they want the chemical formula for calcium oxide, because that's what let's look at the solution here. So calcium chemical formula. So chemical formula for calcium oxide. So if I look at the, what I can do is I can look at the chemical name here. It says calcium oxide. So I can go to my periodic table here and look at calcium here. So calcium, as you can see, is on this side here, which is Ca here. So I can write Ca. I'm going to have to write the charge that belongs to Ca. So in this case, it belongs in group 2. So this has a 2+ charge here. And oxide, it obviously represents oxygen, right? O here. And oxygen here has a charge of 2-. And because I know the calcium oxide here, I want a net neutral. I can have 1 2+ charge here and 1 2- charge here, right? So 2 plus minus 2 is going to equal 0, which is good. So in this case here, I only need 1 of calcium and 1 of oxygen for me to get calcium oxide. So this is the chemical formula for calcium oxide. You could also figure this out by doing the crisscross method. So you have Ca2O2, and then you can reduce these to lowest terms to make Ca and O. So both of these solutions will get you CaO, which is great. So as you can see, the solution is CaO here. And O does not have a 3- charge, it's supposed to have a 2- here. So they misplaced their kind of diagram here. So let me scroll down so I can see the solution is correct. The charge on oxygen is a 2-, not a 3- like in your diagram here. Solution here is correct. Okay. Number 8 says name the following alkyne. Redraw this. Carbon, triple bond carbon, and then carbon there. Okay, so how do we name this? Well, what we're going to do is we're looking at the alkyne group. We want to minimize the number here. So what we're going to do, we won't start from left to right, but we're actually going from right to left because we want to prioritize this alkyne group. We want to make the carbon, the number of the carbon here, the least, or the smallest numbers here. So we have 1, 2, 3, this will be 4. Then we can go either up or down. In this case, we can go up for the longest chain, right? So this here would be 5, 6, and 7 here. So we have 1, 2, 3, 4, 5, 6, 7, which is good. So 7 here is our longest chain. And then we have a methyl group on 4, right? So we have a 4 methyl group here as well. So how do we name this compound? Well, we're going to have 4 methyl, obviously. We have 7, so our prefix here is hept, H-E-P-T. And then we have to designate where the alkyne here. And the alkyne here is at 2, right? So hept 2, and then Y-N-E here. And this is our solution for the naming of this compound. So 4-methyl hept 2-ine here. Now, as you can see, the solution is correct. 4-methyl hept 2-heptine works as well. I personally like hept 2-ine because of the newer IUPAC. I'm using the newer IUPAC when I'm naming these compounds because it specifies where the double bond specifically is. So this is hept 2-ine. But this solution works as well. Solution is correct. It would be 4-methyl hept 2-YNE according to the newer IUPAC rules. But the solution is still correct. Let's look at number 9 here. Number 9 is asking us what is the correct formula for the compound formed between calcium and sulfur. So what the compound from calcium, sulfur, sorry. So it's very, very similar to the previous question. So what we can do is we can look at our periodic table. We can find calcium, which is again Ca, which is here. So let me write this in a different color. Ca is calcium, and our charge here is 2+, right? And we can look at sulfur here. Sulfur is here, and it's group 16 here. So we have S here, and the charge for sulfur here is 2-, right? I can do the valence electrons as 8, and I need to minus 2 here to get 6 here, right? So it's going to be 2- here. Again, I could do the crisscross method if I wanted to have Ca2S2, which I can reduce this to simply Ca and S here. Or you can think of it as how many charges do I need to balance out these guys here? Well, I need 1 2+ charge and 1 2- charge, right? Because I know 2 minus 2 is 0. So I only need 1 calcium and 1 sulfur. So therefore it's CaS here. So either way, this is the compound formed from calcium and sulfur, and this will be named as calcium. And then this is an ionic compound, so I will drop the ending and add IDE here for calcium sulfide here. So this is the correct solution for this answer, for this question. Sorry, not answer. And I believe it was multiple choice here, but it says the correct option is A. So let me download this and figure whether or not this solution here is correct. So it's CAS here, which is the correct solution. So this here is A. So indeed, the solution here is correct. Good analysis. And then finally, what we can do is our last question of the day. Here is question 10. And it says, how do you identify the reducing agent in the reaction with magnesium and oxygen? So let me make this a bit nicer here. So I want the reducing agent with magnesium and oxygen here. So I'm going to write out the chemical formula, which is Mg, I don't know the states here, plus oxygen, which is O2, because I know it exists as a diatomic. And I'm going to get MgO here, which is magnesium, magnesium oxide here. If I were to balance this chemical equation, I would need 2 of these guys here, and I would need 2 magnesiums here as well. And this is balanced, right? I have 2 magnesiums on this side, 2 oxygens on the side, and 2 magnesiums on the side, and 2 oxygens. So this here is balanced. This is our balanced chemical equation. I don't like how they put a decimal here, how like putting half here, but this here is okay as well. So again, how do you identify the reducing agent? Well, we can use the mnemonic, right? We know that Leo says GER, which is Juror. And that's how I kind of, I use this mnemonic to figure out oxidation and reduction. So Leo is loss of electrons. So LEO is Leo, kind of. LEO maybe is oxidation, oxidize. And gain, if I gain electrons, it says it's reduction. So it's going to be an electron. It's going to be an electron. You can think of it as an electron contributor here. You can think of it as it says the oxidation reaction takes electrons, so you lose electrons, and it's reduced. So therefore, it's electron acceptor here. So wait, let's see. An oxidizing agent takes electrons, and the other species is reduced. Therefore, it's an electron acceptor, which is good. A reducing agent is electron contributor, so it gives to other species and is oxidized here. So in this case here, magnesium is converted to MgO, right? So I'm losing, again, I have Mg2 plus here. You can think of this as Mg2 plus, and I'm losing these electrons. I'm going to lose these electrons to oxygen here, because oxygen is our 2 minus, right? So these 2 plus charges, I'm going to lose 2 electrons, and oxygen is going to gain 2 electrons here. So in this case, magnesium is converted to MgO here. Magnesium loses 2 electrons. Oxygen is going to gain 2 electrons here. Okay, so this is good. So the reducing agent here is, this solution here is not correct actually, because it's the reducing agent here is oxygen, because oxygen is the one that's gaining electrons, because this here I'm losing electrons here. The loss of electrons here is our oxidation, and magnesium, or sorry, magnesium here is oxidize. Here's our oxidation. Our oxidizer is being, because again, I'm losing electrons on magnesium, right? And then my oxygen here is gaining electrons here. So therefore, gaining electrons, again, I said it's reduction. So therefore, oxygen here is my reduction agent. So this solution here is incorrect. Let me try to figure out what a good mnemonic is. I use Leo and Juror, but there might be a better one for you as well. So just give me a second while I look for this guy here as well. Okay. Wait, hold up. So let me erase this. So oxidizing. So Leo says Juror. So losing electrons is, you can think of this as, if I'm losing electrons here, my oxidation state is going to increase here. So let me rewrite this here. Oh, actually no, I think the solution is correct. So it says loss of electrons here. Leo says Juror. So again, a reducing agent reduces other substance and loses electrons here. So if I'm losing electrons here, this will be my reduction. So this here is my reducing agent. And this oxygen here is gaining electrons. So therefore, it's going to be, my oxidation rate is going to decrease. So this here is going to be a reduction here. So let me erase this. And I think I'm going to use oil rig as well as my other one. So I think this one's a little bit more misleading. So I'm going to use oil rig here. So oil rig. So oil is oxidation, is again I and L. So it's loss of electrons. So I'm losing electrons. And then R here means reduction. And the G just means gain electrons. So in this case, which one's losing electrons? Well, as you can see, oxidation is losing electrons here, and reduction here is gaining electrons, right? So in this case here, Magnesium here is the reducing agent. And oxygen here is going to be our oxidation reagent. So magnesium here is the reducing, oxidation here is the oxidizing reagent. So this here is the oxidizing. So therefore, the O2 minus here is going to be the oxidizing agent, and the Mg2 plus is going to be the reduction agent. It's a little bit confusing, but again, you can use this mnemonic to help you memorize this, but you can also use the fact that halogens are usually halogens and other kind of non-metals are always tend to be the oxidation agent, whereas alkali metals and alkaline earth metals, you tend to be the reducing agent here as well. Because again, reducing agent, I'm gaining electrons here. So this solution here is correct. So that was a confusion on my part. So that's my bad. Good analysis here. So that's going to be the end of my video for today. Again, thank you so much for watching this video. As always, I stream on Monday and Wednesdays. Monday would be math and chemistry is on Wednesday, so you can check me out then. Again, thank you so much for watching. Stay safe, stay healthy, and have a great day. Take care.